Hello, in this video I want to design and build a dual rail linear bench power supply. My requirements are it must be a low noise linear design, something you would use for designing circuits with op amps or maybe discrete use of transistors. The minimum output should be plus minus 20 volts and minimum output current should be 500 milliamps, and the voltage must be adjustable from 0 volt up to the maximum, also called constant voltage mode. And same with the current, we must be able to limit the current from anywhere from near 0 milliamps up to the maximum output current, also called constant current mode. Okay, let's have a quick look at the schematic for the design I've come up with. It is fairly simple, and to keep it simple I've decided to use standard linear regulators. So the regulators I've gone with is the most common LM317 and LM337. So what we have here is the positive rail up here, and down here we have the negative rail. So let's just run over the how it works really quickly. On the input here we have AC input for a transformer, so something between 18 to 24 volt AC input, either two secondary windings, or you can use a single secondary winding with a center tap as well. Then we have a dual bridge rectifier, we have some smoothing capacitors, and if we zoom in here a little bit, the first regulator here is to generate a plus 5 volt, and the second regulator is for the constant current regulation, and the third regulator here is for the constant voltage output. And we have a couple of pots here, 1K for the current adjustment and a 10K for the voltage adjustment. To set the maximum output current, these three resistors, so currently it's 3.9 ohm resistors, half a watt in parallel, giving 1.3 ohm resistor, and that gives a maximum current output of about 950 milliamp in this configuration. But you can change the values of these resistors if you want to adjust how much output current you want. And the reason for the constant current LM334 constant current sink here is to make sure we can regulate all the way down to 0 volts, and the same here with the minus 5 volts. Instead of connecting it to ground as you usually would, is so we can regulate the voltage all the way down to 0 volt instead of the usual 1.25 volt limitation. And if we look at the negative rail, it's all pretty much, well, it's exactly the same design, just with LM337 and being configured for negative output. So the core of this design is actually based on a small application note in a data sheet. We can take a quick look at that. Here it is. So you can see it's basically the same design with a few small changes. In the original design they use a JFET for a constant current sink here, but since JFETs are not that common components anymore, I replaced that with an LM334. And for the voltage adjustment, they also use a JFET here, but we don't really need that. As long as the negative voltage we have here is fairly constant, and we can just replace it with a resistor, because most of the current is going to run through these diodes and then be limited by a resistor here. That will work just fine. So the purpose of these two diodes here is to create a voltage drop of approximately 1.25 volts to compensate for the internal reference 1.25 volt reference in the LM317. And the same over here, these two diodes here together with the constant current to give the voltage drop of approximately 1.25 volts. So it will keep this point here approximately 1.25 volt below the output here, and allowing us to adjust all the way down to 0 volts, and the same here, adjust the voltage output all the way down to 0 volts. So if we take a look at the data sheet for the LM317 regulator, we can see it sounds pretty good. Output current excess of 1.5 amps, adjustable output voltage between 1.2 and 37 volts, and it's got internal both thermal protection and short circuit protection. However, there are a few things we need to understand. First, the maximum input-output voltage difference is 40 volts. So that means we could not have an input voltage higher than 40 volts if we want to be able to regulate all the way down to 0 volts. And another figure we need to understand is that the maximum operating junction temperature, so that's the internal temperature, is 150 degrees Celsius. And then we need to see the thermal resistance internal to the case, junction to case, is 5 degrees Celsius per watt. So that means we're dissipating 10 watts in our regulator, then there will be a difference of 50 degrees between the internal temperature and the outside heatsink temperature. So that means we have to add the ambient temperature and the rise of temperature and the heatsink and everything. That means we're probably going to be limited to something like maximum power dissipation around 15 watt is probably realistic. Absolute maximum is probably 20 watt, but realistic 15 watt maximum dissipation in the regulator. So that is quite important when we make our decisions on how much output current we need and how much output voltage we need. Other than that, we have some performance figures here. I mean, it's good to know. And also we should have a look at this chart here. This is the dropout voltage. So this is not a low dropout regulator, so we should expect to have a voltage drop per regulator, something around 2 volts is probably realistic. We're not going to go above 1 amp here, so around 2 volts drop. And temperature, well, we're probably not going to be operating at minus 50 degrees Celsius, so somewhere from room temperature up to the absolute maximum temperature rating, so around 2 volts voltage drop. So what we have here is the board layout. It's quite simple. We have our input over here for our transformer, secondary side of our transformer connecting over here, our bridge rectifier diodes here in the center, and then we have our smoothing capacitors here, and everything up here is for the positive rail, everything down here is for the negative rail, and we have some connectors for our potentiometers, and we have the output here and potentiometers for the negative rail. So I decided to go through-hole components on everything here, just to keep it quite simple. And for reference, here is a quick look at the board I made. So this is the top side, and this is the bottom side. And here I've started assembly. So with through-hole parts, or generally when you're soldering things together, it's best to start with the lowest parts first. So here comes all the resistors and the diodes. And because this is a homemade double-sided board, I have to manually solder in wires as well. And here adding the next layer of components, start getting the input terminals, the output terminals, some capacitors. And one thing worth noting is these capacitors here, so these are 1 microfarad film capacitors, and I really recommend using film capacitors here. These are the capacitors for the output of the final regulator, and using a film capacitor will give you a better performance than using an electrolytic capacitor. And here we have the completed module with all the components installed. I think it came out quite nice. It's a nice little compact module here. Of course, we are going to need some heat sinking on both sides here. But I think first of all, let's try to do a quick test and see if the functionality is correct, because it's easy. I might have made a mistake somewhere. So I hooked up 2 bins power supply to try test it here. So power supply number 1 is connect positive here and negative over here, and power supply number 2 is connected positive here and negative over here, so basically giving a negative voltage input here. So I use Ben's power supplies for testing because I can current limiting them, so in case I have something that's short-circuited here, it's not going to do any damage. However, if you don't have two bench power supplies you can use for testing. You can also just use the transformer you're going to hook it up. However, I recommend connecting a 100 ohm resistor in series with the positive input over here and the negative input over here to limit the current in case you have some kind of problem. And on the output, I've connected 2 meters, one on the positive side and one on the negative side. So I haven't connected any pots up yet. I just want to see if we get some kind of voltage out here. So in theory, we should get something like, I think I had a power supply set to about 15 volts and we will have some drop over here. So maybe we'll get something like 11, 12 volts out here and minus over here and positive over here. So let me try switch on my power supplies and see what happens. Yeah, there we go. 12 volts over here, minus 11.9 over here. There can be minor differences between the two because the internal references are not very precision in these regulators. Okay, so I've hooked up some pots here. I'm just using dual pots so I can control both voltages with one pot here. Well, this is the current and this is the voltage. But it's really up to you how you want to configure it. You can also do single pots for both voltage and current for each side. You can adjust it more accurately this way because these are not going to be super accurate potentiometers. You will have a little bit of a difference between the two voltages and the two currents. Anyway, let me try switch on my power supply again and we can see if we can adjust the voltage. There we go. That's definitely different voltage now. We can try to turn it up. Yeah. Turn the voltage down. Yeah, you can see that seems to be working okay. We do have a slight difference between the two sides, but that's kind of to be expected because there's some difference in the potentiometers here. They're not going to be 100% accurate, and there are going to be some differences in the references, in the regulators here, and a little bit in the resistors. So I think that's quite okay. That seems to be working. Okay. So the voltage adjustment seemed to work fine. So let's do a test on the current and see how that goes. So I've upped the power supplies to about 200 milliamp limiting now. And I think we can just go in the milliamp setting on the 2 meters here. And we're going to move down here. See what the current's saying. Minus 20, 17. Again, there are going to be slight differences in the currents, but I'm just going to try adjust it here and see what happens. Okay. Oh, it seems pretty good. That's like 110, 113 milliamps. Definitely the adjustment is working. Now the power supplies are going to go into constant current mode, limit the current because we're getting close to 200. But that seems to be working fine, so I don't want to push it any harder because we don't have any heat sinks on these regulators here, so they will get very toasty. But functionality wise, this seems to be working. So I think it's time to find some heat sinks and see if we can stuff this thing in a box and then hook up the correct transformer, and then we are pretty close to having a functional power supply. So it's time to put some heat sinks on the little power supply module here. So it would be very tempting to just put 6 of these little heat sinks on, but unfortunately they're not big enough. We need something more substantial. I do have something like these here, but I think there are 2 problems. One, well, the cooling fins here are in the wrong direction, so it's not going to be optimal, but also there's not very much mass in these, so I think still these are not quite big enough. So the next thing I have is something like this heatsink here, some kind of surplus or something I picked up at some point. So of course it's pre-drilled for a TO3 transistor, but I think if I cut it in half see how big is this. It's like 80 times 110 millimeters, so it'll be like 40 times 110. I think that would make a fairly good heatsink, but I do need to cut it in half. Also, we need a transformer to make the whole thing work when we connect it to the mains. So originally I had planned to use one of these little things here. That is well, we got two primary windings, 120 volts here, but we can just put them in series, and then it's 240 volts. And on the secondary, we have two 18 volts windings. So that would give us something like 24, 25 volts after a full wave rectifier. So that means the maximum output would be about plus minus 20 volts from the power supply here. However, this is only rated for 30 VA volt amperes, so it's a little bit on the small side, but it would work fine. So I picked up another transformer. So this is a 50 VA. We got the primary windings here, 240 volt, and then we got the secondary, so it's a center tapped secondary winding. And so it's 24 volts, 24 volts. So that would just go in here. And that should give us, I think after rectification, there will be something like maybe 35 volts. And then we'll have some ripple we need to get rid of. And that should give us something close to 30 volt output maximum here. But one thing, keeping in mind that if we have 35 volt on the input here, then it's limited how much current we can get out of it. So really the safe operating error will only be something like 500 milliamps if we're gonna drop the full 35 volts across these regulators here. However, if let's say we want the output to be like plus minus 16 volts, then it could probably support full amp out. So need to decide what we'll do about that. And of course we need to put everything in a box. So I have found this box here. It's a nice small size. I think it should work okay. Should be able to fit everything in here, hopefully. So it might be a little bit tricky if we need this big heatsink here. Maybe we can, I think if we turn it around like this, then it should fit. Yeah, I think that's how I want to do it. So I think this will still be okay. Might cut a little bit off here on the heatsink as well. Yeah, just give a little bit more space, but I think it will work. Of course, there's not going to be much space here on the front panel, so I do need some meters here so we can see the current and the voltage of the outputs. But of course, since we have, it's going to be a dual rail output plus and minus, really we need 2 voltmeters and 2 amp meters, and we could go with some digital meters like this, but I think this is like a nice old school power supply design. So I picked up some, see if I can find them here, some analog meters. These were the smallest ones I could find. Here we go. These cute little meters here. I mean, they're not going to be super accurate, but it should look quite nice. Of course, the problem is, I can't fit 4 in here, but then I still need space for 2 pots, and I need my output terminals as well. So I think what I'm going to do is put in 2 amp meters and just 1 voltmeter, and maybe have a switch where we can switch between positive and negative viewing the voltage, but amp you'll always be able to see the actual current draw for both the positive and the negative output. And then we should have enough space for our potentiometers here. And I think it would be nice to have an on-off switch, and then we need a switch to switch between the two voltages. And I think it would be nice to have a switch as well, so we could kind of set the current, because we need to short the outputs. We need to short the outputs here to set the current. Okay, I've cut the heatsink in half, and I drilled the tap 3 holes on each side here, so we can fasten the regulators to the heat sinks. I really did have an option here to drill and tap because there's not enough space in here to have a nut on the other side, but I have to say I really hate tapping small holes like this. It usually requires a lot of alcohol, not just for me, but also to lubricate the tap here, make sure it doesn't bind in the aluminium. But small tap like this, it always feels like it's going to break any second. It's so tiny. Anyway, it was successful, so next step is going to have to be mount the heat sinks on the board here. However, one thing you have to be aware of is that the tap here on the regulators is always connected to pin 2, the center pin on the regulators. So that's going to be on the LM317 is going to be the output. That's going to be on the tap here, and on the 337 is going to be the input. So that means we need to isolate them from the heatsink. We can't just short these together. It would just short everything out. So we're going to need some of these little sill pads here. I think these are for TO220 packages. Yeah, that fits fine. And some of these little isolation things here for the screws. So it just goes in like this. Then we put it on the sill pad, put a screw through and screw it in, and then it'll be isolated from the heatsink. And just to make sure we have a good thermal connection, I'm going to put some heatsink grease on both sides of the sill pad here. So let me just do that. Okay, so I got the heatsinks mounted here with the sill pads and heatsink compound. It's looking pretty good, but well, it is starting to get pretty big now. So see, I hope it will still fit in the case here. Yeah, doesn't look too bad. I might have to cut a little bit off the heatsink because the meters here, they're fairly deep. So I think I might have to trim just a little bit off some of the fins here, but not a big deal. So I think next is to start looking at the panels here, front and back panel. So I would like to get this connector in the back. It's nice IEC. It's got a built-in fuse here, and we got a switch, and it's a 2-pole switch. So we're gonna be switching both neutral and live. So it should be extra safe, and we got a ground connection as well. So if we get that to sit over here somewhere, I think that would be pretty ideal. So I need to cut a square hole in this little panel here. Luckily this is just thin aluminium or something like that. It should be quite easy. And also I've come up with a design for the front panel. So I have this template here, and I'm just going to cut this out and glue it onto the front panel, and then I can start drilling and cutting out all the holes I need in the front panel. So the design is going to be like this. It's going to be a voltmeter over here. Going to have 2 amp meters here and here for the positive and negative, and then we'll have switches like these. One here to short the output so we can set the current, and this one is for the voltmeter so we can switch between showing the positive and the negative voltage. And over here we will have one more switch. It's just going to be on off. It's just going to disconnect the outputs, and then we're going to have our pots here for current and for voltage. So I think that's going to be quite nice. And of course we're going to have our three output terminals here: positive, ground, negative. We could put a mains ground in here as well, but I don't think, I rarely use, most power supply have a mains ground plus a ground output here, but I rarely use it. So I think if I need something connected to mains ground, I'm going to keep this on floating, but if I need mains ground connection, I can always take it from one of my other power supplies. So I have cut out and glued on my templates on both the front and the rear panel here. So it's time to start cutting out all these holes and drilling and so on. So I think, I don't have a step drill that's big enough for these round holes here. So I think it's gonna be like the old technique of just drilling a lot of holes and then afterwards just following up with a little bit of manual filing, or maybe I can grind it or something. The square hole here, I think we just use like a Dremel cutting disc or something like that. I'm not going to record that. I don't think it's going to be very interesting. Okay, so I'm done drilling and filing, and I've just test fitted all the parts here. I think it came out quite nice. Everything fits really well. Let's see here. So it was a bit of a chore to get these big holes drilled out for the meters here, because I had to manually file them to size, but at least it's pretty thin, this panel here, so it's not too bad. So next will be to get everything wired up. So I think I'm going to start with this socket here. Just get that wired up with the transformer, and then we can start putting everything together. Okay, so let's have a look at how everything is going to be wired up. If we start over here with the mains input, live, neutral, and ground. So we say this is the IEC socket here, right, where the mains comes in. Ground is gonna go to the chassis. Because we have a metal case, we should always connect ground to the metal case for safety reasons. And then we have live coming in here. First thing it goes through is a fuse. Then we have a switch, and it's going to be the same for both here. This one switch. Then we go into the transformer, and from the transformer, so in this case here we have a center tapped secondary. So it just goes like this, so then we have a center tap here. But it could also be like two separate windings. It will give the same result. We have the main board here. So there are 4 terminals on the board here, but really the two center terminals, they're just connected together. In case you have 2 windings here, you can connect all 4 wires, but you only have a center tap secondary. Just connect the center to either of those 2, and the other 2 wires to the outer terminals. Then we have 3 outputs here: plus, 0, and negative. And the first thing we're going to go through is the amp meter. That's going to be both on the positive and the negative output. And then we have the ground running through here. And then we'll have our first switch. That's going to be the set run, or the current set switch. So we draw that something like this. And the way it's going to work is that it's going to short to the ground. So basically it'll be like this. So instead of having the switch the other way around, so it will just short everything to ground, this way it will disconnect the output. So it's not going to short the output to ground, it will only short, well, it's not going to, the power supply output, the external output, is not going to be shorted to ground, but the output from the power supply board here will be shorted to zero, right? The reason I do it like this is because you might have a battery attached to the power supply, and you probably don't want to short your battery when you want to set the current. So this way it will disable the outputs when it gets shorted, so there's no risk. And then we continue out here. We have the on-off switch. Like this. So this is on-off. It will simply just disconnect the output. So these are connected together. This is one switch with two poles. And then we have the power supply outputs here, right? There's positive, 0, and negative output. And then we have the voltmeter. So the voltmeter is a little bit tricky because I'm only going to be using 1 voltmeter. That means we have to reverse the polarity when we switch between the two rails. But we can still do that with a single switch. We just need to do something like this. Well, this is going to be the voltmeter here. And then we have our switch here. And that will be our positive, negative switch. Let's see if I can draw this like this. Okay, and then the last one here. Let's see, that is correct, right? Yes. So this will reverse the polarity of the meter here. So we have to think about there's a positive and negative. And when we do the negative wheel, well, we have to have the negative wheel because it's going to be more negative than our 0. So we have to reverse the polarity of the meter, but we can still do it with a single switch here. So that's basically it. This is how everything is going to be wired up. Okay, so I wired up the primary side of the transformer here. It's all looking good. And for the front panel, here, I have replaced the drilling template with the final design here with some text, a little bit of graphics. This I just print on normal paper, but then I coat it. I give it like 3-4 coats of this polyurethane satin finish. It changes the paper. It becomes a very strong surface. Polyurethane finish is very durable, and it gives like this nice satin finish. It almost looks and feels like a professionally made front panel film. So I think that looks quite nice. A couple other things I need to address, because the scale here on the voltmeter is not correct. It has to go to 30 volts. It's not a big deal. Scanning the scale here, I will just modify it, print it out, and then I'll use the same method with polyurethane and create a new scale that goes to 30 volts. So while I'm at it, I think I'll also change the scale on the amp meters. I still want to go to up to 1 amp, but I think I want to indicate that everything above 500 milliamps is outside the safe operating area. Okay, I've wired everything up here. Try to keep a little bit neat and tidy, but it's quite a lot of wires in the end. And also I have changed the scales here, so now we go all the way to 30 volts. So of course, to make the meter changes from a 20 volt meter to a 30 volt meter, I had to add a series resistor. I think it was like 8.2 kilo ohms. Ended up being the perfect resistor to make it go to 30 volts. And while I was at it, I changed the scales for the 2 amp meters as well. Just indicate negative, positive here, and kind of give an indication that everything above 500 milliamps is kind of in the unsafe operating area, both of them here. So I think that came out quite nice. And I've started drilling a few holes and stuff in the case here. So all we have left to do is just to put everything together. And finally we have everything put together. Everything has been screwed in now, fastened, and it all fit in this case here. I did have to cut a little bit off the 3 fins here on the heatsink, but nothing major. So everything is very solid now. The heat sinks are screwed in, the board is screwed in, the transformer is screwed in. So all we need to do now is put a top cover on, and then we can give it a quick test and see how it works. So here we have the completed power supply. I'm just going to switch it on the back here. Obviously none of the meters changes. Try to turn up the voltage here. Yeah. Seems to work well. And then we can set the current over here, and we can see if we want, for example, current limited to 200 milliamps, and we would set it here, and then we switch it back here, and now the power supply is limited to 200 milliamps. Here I have a small load. This is I think about 20 ohm resistor load on a heatsink. I've just connected here just so we can see that now it goes into constant current mode. And if we up the voltage here, nothing is going to happen. But if we up the current here, it's going to increase the voltage as well. And we can see currently we only have a load on the positive, so there's no output on the negative here. And we can see if we switch the negative here, right, so we'll have like 20 volts here, and here we have 10 volts. And we can try to switch it off here, and then we can see it goes up to 20 volt. Switch it back on, and we're down to 10 volts again. So that means the constant current and the constant voltage is working as expected. So I will do a full set of tests of this power supply, just so we know exactly what the performance is like and what to expect. However, I think this video is long enough already, so I think I'll do that in a separate video. So if you're interested in building a power supply like this, there's a link in the description where you can download all the details. And if you have any questions, feel free to leave a comment. I'll try to reply as quickly as possible. So I hope you enjoyed the video, and thanks for watching, and I'll see you next time. Bye bye.